In this lesson, we are going to be completing dimensional analysis, in which you will be able to convert from the mass of one substance into the mass of another substance in a reaction. Now, you should have completed this in first year chemistry, so most of this should be review with just a couple of new concepts added in. Alright, so here are the conversions. If I have mass A, so I have the mass of substance A, what I need to do in order to convert it into the mass of substance B, I first need to convert it into moles of substance A. Now, in order to do that, I need to use molar mass. Now, to go from moles of A to moles of B, I need to use what's called a mole-to-mole ratio. And you get that mole-to-mole ratio using the coefficients in a balanced reaction. Now I'm in moles of B. To convert to mass of B, I again need to use the molar mass. So notice that there are a number of steps. You have to go from the mass of substance A to the number of moles of substance A to the number of moles of substance B, then to the mass of substance B. Just keep in mind that the units are crucial in making sure that you can do that properly. If you keep track of your units, these problems should be pretty easy. If I'm given the volume of A, assuming it's at STP, standard temperature and pressure, I can convert into moles of A by using the 22.4. The 22.4 liters of substance A in every mole of substance A. If I want to go from volume of A into volume of B, all I have to do is go from volume of A to moles of A to moles of B, and then into the volume of substance B. Now keep in mind, if I gave you the mass of substance A and asked for the volume of substance B, assuming it's a gas at standard temperature and pressure, you can do that. You can convert from the mass of A to moles of A to moles of B to volume of B. That's fine. You don't have to go just from one volume to another or from one mass to another mass. You can interconvert your units, which is really cool. The last concept is particles. Remember, particles includes atoms, it includes molecules, and it includes formula units for ionic compounds. To convert from particles of A to moles of A, I need to use Avogadro's number, which is 6.02 times 10 to the 23rd. And then again, to go from moles of B into particles of B, I need to use that 6.02 times 10 to the 23rd conversion as well. So I can go from particles of A into the mass of B, into grams of B, by just going from particles of A to moles of A to moles of B to mass of B. So converting between different units is possible as long as you follow this conversion path. Make sure you're not going straight from mass of A to mass of B. You've got to first convert to moles so that you can use the mole-to-mole ratio in order to convert from moles of A into moles of B. This problem tells you that you have 67.2 liters of nitrogen and it's reacting with hydrogen, and what it wants to know is how many grams of ammonia are going to be produced. In order to complete this, this is a stoichiometry problem, and specifically I'm going to have to convert from liters of nitrogen into moles of nitrogen and then be able to get into grams of NH3. Now, to go from terms of N2 into NH3, I need to use my mole-to-mole ratio. Notice the first thing you should do before completing a problem is note that this reaction is actually already balanced for you. So if I start off, I have 67.2 liters of nitrogen. Notice I'm talking about a gas and it's at STP. If it were not at standard temperature and pressure, I would not be able to assume the relationship I'm about to assume. The first thing I want to do is get into moles of nitrogen. In order to do that, the relationship between liters and moles at STP is 22.4 liters for every 1 mole. Now I need to go from moles of nitrogen into moles of NH3. So I'm going to put moles of N2 on bottom. I'm going to put moles of NH3 up top. This mole-to-mole ratio is based on the coefficient. So the coefficient in front of NH3 is a 2. The coefficient in front of N2 is simply a 1. Finally, I want to get into grams of NH3, so I'm going to put 1 mole of NH3 on bottom, and I'm going to put grams of NH3 up top. The molar mass of NH3 is 17.034 grams per mole. And so when I do this math, I'm going to take 67.2, divide by 22.4, multiply by 2, and then multiply by 17.034. And what you get is 102.0 102.204. Now, this has three significant figures, so I'm going to rely on that for my number of sig figs. So 102.204 should just be 102, that's 3 sig figs, grams of NH3. And that's my answer. The next concept that I'm going to talk about is limiting reactants. Now, before I actually explain limiting reactants in the context of chemistry, I like to use a real-world example. So, if I am going to be making s'mores, and if you look at my reactants, I have 6 pieces of graham cracker. I have a total of 12 chocolate chips, and I have 2 marshmallows. Okay? And in order to make a s'more, you need 2 graham crackers, you need 4 chocolate chips, and you need 1 marshmallow. That's up above. You can see that reaction. So if you notice, based on what I'm being given, I have plenty of graham crackers and I have plenty of chocolate chips because I can make a total of 3 s'mores with the graham crackers I have. I can make a total of 3 s'mores with the chocolate chips that I have. However, I can only make 2 s'mores because I only have 2 marshmallows. So if you notice for your product, you can only make 2 s'mores. Notice your marshmallows are completely used up, and now what's left over are your chocolate chips and your graham crackers. So in this problem, your limiting reactant is your marshmallows because it limits how much of your product you can make. I can only make 2 s'mores instead of being able to make 3 s'mores like I could have if I had more marshmallows. So in this section, we're going to be talking about limiting reactants, which is extremely similar to this analogy. The limiting reactant is the one that limits the amount of product that's formed. Now you have also excess reactant or excess reactants, as is in this case, and those are the ones that are left over after a reaction occurs. So in this problem, your chocolate chips and your graham crackers are your excess reactants. By reading this problem, you should be able to recognize the fact that it is a limiting reactant problem because you're given 2 different quantities of reactants and you're not sure which one will be responsible for the amount of product that is formed. So if you notice, you're given 1.5 moles of aluminum and 3 moles of chlorine. And so what you need to do first, in order to determine how many grams of product are actually going to be formed, you need to figure out how many grams of product each of these can form. In order to do that, I first have to balance the reaction that is occurring. So I have 2 chlorines here and 3 here, so I've got to put a 2 here, a 3 here, and a 2 here. And so what I'm going to do now is I'm going to calculate the number of grams of product of aluminum chloride that each of these reactants will produce, and that will enable me to determine which is the limiting reactant. So in this problem, I have 1.5 moles of aluminum, and I want to calculate how many grams of aluminum chloride that will produce. So I'm going to put moles of aluminum on bottom, and I'm going to put moles of aluminum chloride up top. Finally, in order to get into grams, which is what I'm asked for, I'm going to put that up top, and I'm going to put moles of aluminum chloride on bottom. So I need to put my mole to mole ratio right here. The coefficient for AlCl3 is a 2, for Al is a 2, and then I need to put the molar mass of aluminum chloride, which is 133.33 grams for every 1 mole. And so the mass of aluminum chloride that's produced is 199.995 grams. And now I'm going to do the exact same thing but for chlorine. So if I have 3 moles of chlorine, then I need to first convert from moles of chlorine into moles of aluminum chloride. So I'm going to put a 2 for the coefficient of AlCl3 and a 3 for chlorine. Then I've got to convert to grams. It's the same as what I had above. And 1 mole. And so what I get for the mass of product that is formed from chlorine is 266.66 grams. So based on the s'more example, aluminum can only produce 199 grams before it runs out, while chlorine can produce a total of 266. So what that tells me is that aluminum is my limiting reactant because it limits the amount of product that will form. Therefore, to answer the question how many grams of product are formed, it would be this value right here. Now be careful because 1.5 moles only has two significant figures. So I can't really round this while keeping it in standard form, so I've got to convert it into scientific notation. So to make 2 sig figs, it becomes 2.0 times 10 to the second. That's just 200 grams. Okay. Now, one other alteration that I can provide is instead of giving you moles of your reactant, I could give you grams of reactant, right? So we could have started here with grams of reactant instead of with moles. The problem is only one step short of that example. So all you have to do is then convert into moles and then continue on. The whole point of these problems, they're extremely similar to what we worked on before. The only difference is that now you're creating two different amounts of products. The one that forms the least amount of product is the one that limits the product, meaning it is your limiting reactant, and therefore that is how much can actually be produced. Even though chlorine could make a total of 266 grams, it doesn't matter because aluminum is already used up, and therefore no more aluminum chloride can be produced.